Well, let me start by saying that, well, let me just clarify something. As you can see, the title of this presentation is The Space Age from 1960 to 1990. And you can ask the question, why did we stop at 1990? Because it's only 3 decades. Well, this decision was made by the executive committee who told me that whatever happened after 1990 is something what everybody in this audience should already know. Now, whether this is true or not, but in any case, this presentation of history will be rather, I would say, intensive. It's going to be incomplete, and it is kind of a personal view of these 30 years, kind of snapshots of what happened during those 30 years. Now, if I left out something from the history, I wouldn't worry about it too much, because I was told by somebody that history repeats itself. So we'll see. Maybe true, maybe not. I have to find this. Okay. The presentation basically will cover these 3 topics: the human activities, the technology, and investigations by decade. And if I can just focus for a moment on the technology, I would like to just say that most of the technology which was used by geologists was really invented by others. And there were just very few instruments which you could consider truly invented for geodesy. One of them is the level, and the other one, the torsion balance, which was already mentioned here. All the others were really invented by others, and geodesists, if you like, simply learned how to make use of them, or if you like the word, kidnap them. The second part, this is this investigation part, is also an interesting thing, because clearly when the observation started, regardless of what kind of an instrumentation, the results of the observations really were kind of curious and had to be explained. So this is where really the theory and modeling came into the picture, just to see whether the phenomena we see in the observations really can be explained by appropriate modeling. And then, of course, after the modeling was done, then it turned out that the modeling shows certain things which the observations haven't seen yet, and this led in turn to further improvement in technology. And this cycle kind of continued, and I will try to show you a little bit how these things went hand by hand. And finally, the general activities really is more for the IAG. Really, especially during these 3 decades, it was the IAG which provided home, if you like, or an umbrella, all these symposia and organizations and general assemblies to best utilize these techniques and the models, theory, also to provide incentives and to improve both the observations and the theory. There are many, of course, examples of this. Another purpose of these meetings, of course, is to teach. And I think the teaching part is very useful for both the young generation as well as the old generation. So, let's get started. If I can push this. Nothing happens. Okay. I just go back for a minute to the 1950s, which was a really broad point of time period, simply because it was in 1957 really when the first Sputnik satellite and the Vanguard first satellite went into orbit. And very quickly, of course, in 1958, is really when, what you can say, the satellite geography started. It really started by the so-called Moonwatch teams. I don't know whether you heard of them or learned of them. Moonwatch teams were really students at different universities which were lined up on a meridian with a telescope in their hand, and were watching whether something would go through the meridian. If it did, they timed it, and this is really how the very first observations for satellites done. The Smithsonian Astrophysical Observatory developed a beacon camera system already then. In fact, the first one, already in 1958, was deployed in New Mexico. And it was during that time period when the transit Doppler system was sort of, at least thought about. This picture here shows the beacon camera of the Smithsonian in New Mexico. This is what we call a tracking camera. The tracking means that it could be moved both in the sidereal array as well as the satellite array. So they were simply trying to follow the satellite timing in the direction. During that same time period, there was still great emphasis paid on the accuracy of baseline measurements, and therefore a lot of effort went into the electronic distance measuring techniques. And this picture simply shows from 1959 a demonstration of one of the, that time, very up-to-date instruments. And some of you will probably recognize some people, although I'm sorry to say that none of them are alive. Well, you will see a lot of people here who are no longer with us, but nobody in those fancy uniforms, general uniforms that you have seen in the first presentation by Mr. I should also say, since from the 50s, I should like to point to this particular item here. George Weiss, who many of you know from Greece, in 1958 wrote his dissertation, which was called Geodetic Applications of Observations of the Moon, Artificial Satellites and Rockets. And this was probably the very first comprehensive treatment of how to use satellite observations mainly for geometrical. This thing was actually a dissertation at Ohio State University, and then it was published by the Smithsonian. And it is, I really consider it one of the fundamental publications which will have value for our day. You can also see that those first observations with cameras were not terribly accurate. And the positioning was only about 100 meters, absolute and maybe 20 meters in relative. But what really was a revolutionary thing was the discovery that actually the Earth's gravity field has a J2 and a J3 harmonic coefficient. The J3 indicating that the Earth is after all not just a one sphere. Right? This is how the term pear-shaped Earth or potato or whatever came about. Just for interest, I found this old photograph, which is from that time period, the IMF is Geodetic Division. And this gentleman here in the center is John O'Keefe, who discovered the J3. Equally interesting probably to some of you, maybe recognize the face. This is William Cowell, whose name was mentioned already on several occasions. And in between is Søren Henriksen, whom later, I will talk about him later. Okay, so now we're in the 60s. That's really when I started. Okay, 1960 was the Helsinki General Assembly. The president during that was elected Charles Whitney, and General Secretary, as you can see, following Tardy, as mentioned by Bob, was Epilogue for 15 years. And I will talk about him a little bit later because he was really a remarkable person and the first Secretary General I had personally. In 1963, the Berkeley General Assembly and the president who was elected was Roy Montfort from Argentina. Just to show you how old I am, I have to confess that the first General Assembly I attended was the Berkeley General Assembly, which was exactly 50 years ago. So a quick arithmetic will tell you that I am at least 50 years old. Okay, this is the President Montfort, between 63 and 67. He was a brigadier in the British Army. Later he became professor at the Oxford University, and probably most of you know what about the book what he published. It was a book about this trip for Montfort's geodesy, and it had 4 editions. The last edition was published in 1980. So it was a very, well, for us it was the Bible. Now, 50 years ago, more or less, because they could never agree whether 62 or 63 was the 100th anniversary of the IAG, and this is the celebration. This is Wiki, and this is Levallois, as I said, whom I mentioned earlier, and here is Professor Kneissl, who at that time was the, how shall I say, Pope of the German geodesy. And here on the other side is Gardi. And in the background, probably you, well, certainly most of you from Munich will recognize that this is one of the frescoes in the Hercules Saal. Now here is Levallois. I have to say that this picture I just got from Paul Boucher yesterday, and I managed to put it into the PowerPoint presentation, which was quite an achievement. And I was really worried that because of that you are not going to have a lecture here. There it is. Okay, Levallois was probably one of the most remarkable men I ever known. Best way to tell who he was in the IAG, I would say that he was probably a benevolent dictator. And all the presidents and everybody else on the executive committees, when he called them, they said, yes, sir. And literally, he ran the IAG for those 15 years with some help of the presidents and some of the others. He was a very nice person, and, well, we are missing. Well, you already heard about these people. They were there at this anniversary. Walter Lambert, the architect on the left, and Benning Magnus and the Graf Hunter. They are a little bit older here than in the pictures what Boucher showed. Interestingly, Walter Lambert is holding a briefcase very close there. I wonder what was in there. And behind him there is an interesting looking bottle, which I'm not sure what use they made of. Okay, here we go. Okay, general activities. 1963, the International Polar Motion Service was set up to be continuation of the International Latitude Service. In 1963, the Central Bureau for Satellite Geodesy was established in Cambridge, Massachusetts, mainly due to the effort of George Rice and Gaposchkin and Isaac, who were really doing an awful lot of work at the Smithsonian at that time to determine more and more of these professions. In 1966, there was also a Marine Geodesy Symposium in Columbus in 1966, which was probably the first of a kind. Then the Lucerne General Assembly came about, and the president, Antonio Marussi. Now, Marussi was also one of the most remarkable scientists, not just as a president, think his book on intrinsic geodesy, I don't know whether you read it or seen it, again, is one of the fundamental books, I think, that should be on the bookshelves, or at least in the libraries. Second symposium, well, now I'm just going to show you some of the symposium, not some of the meetings where people excuse me, participated and learned and talked and improved things. This one, for example, was in 1966 International Symposium in Brussels on non-geodetic calculations. Oops. Anybody recognize this? Moritz. Well, I'm not sure whether he's calling order to a meeting or whether he was simply this picture here is the symposium on continental drift, secular motion of the pole and the rotation of the Earth, which was in the beautiful place at Stresa in Italy. And this meeting is probably significant from the point of view, but as far as I know, this was the first time when placing the coordinate reflectors on the moon was suggested. And of course, as you know, later this became reality. I'm not sure whether you can recognize somebody that you have a better view than I do, but there are some interesting people in here. Okay, for example, this person here is Paul Melchior. He is famous for his dive work, and of course he was at that time the General Secretary, I think, of the International Union of Geophysics. Probably some of you are from the Bonn area, recognize this gentleman. And so forth. He started. Not sure why he was there. But anyway, so this, as I said, this meeting was primarily to push the lunar laser effort, and of course some of the other things as well. Technology. You will be surprised to see that in the 60s how much effort really went into developing absolute gravity meters, presumably or hopefully even transportable absolute gravity meters, because obviously the gravity network, the importance of the gravity network was already recognized, but the absolute values of the gravity or tying the gravity networks together, unifying them was an important thing. So in 63 there was a free-fall interferometric absolute gravimeter with the accuracy which is shown here. This micrometer just went in, that this is one of the electronic distance measurements. The second attempt was a rise and fall. The other one was a free fall, which is a rise and fall absolute gravity meter, which means that they slew up something and falls down. Not that simple. Tens of a milligauss by Cook, and then in 1968, finally there was really a transportable absolute gravity meter developed by Fowler, Colorado, which had an accuracy of about 5 hundredths of a milligauss. And here is a picture of that absolute gravity meter, and you can see, I think, somewhere falls. This thing is falling down. Superconducting gravimeter was another development, and this is really when we are getting into the geodetic satellite area, late 60s, early 60s. And here is a whole series of satellites which were launched at that time. The ANA 1B, the GEOS 1 and 2, PGEOS, Diadem, Oscar Timation. Some of them had flashing lights so that cameras observe them. Some of them had already laser reflectors on them because there were some lasers there. And in 69, of course, the Apollo 11 corner reflector was deposited on the moon, and the first returns at Leak and McDonald observatories were actually received. Now here is one famous satellite, the passive genetic satellite of Aegis, which was just a huge balloon. And you can appreciate the size of this if you look at the man. Now, of course, this thing was not just thrown up like a balloon, but it was packaged, and then of course every after it opened up, and the surface was laminated and it reflected the sun. So again, with the cameras, you could really see this, and they move through the sky, and the cameras chopped it up, and back under the stars, they determined the direction. It was a remarkable thing, and it worked very well, surprisingly, for a long time. This is one of the GEOS 1 satellite, which was later developed GEOS 2 and GEOS 3. GEOS 3 being one of the first altimeter. As you can see, or maybe you cannot see, there are some laser reflectors for laser observations. There are flashing lights, again for camera observations. And then there is a Doppler antenna basically. This one here is actually how it looked like. This brown spot here is probably somebody must have hit it. Not really. This light was used maybe several times, and the last time it was used, they burned it with the projector. I have another one which also very nicely burned, but it shouldn't be like that. Okay. Technology developed. The ballistic satellite cameras were developed. I can talk about this in a minute. Satellite Doppler equipment, first geoceiver in 1969 came about. And then satellite laser tracking really started in earnest, about 1 meter type of accuracy. In 1964 there was the Goddard laser, and others. In 1966, the Smithsonian laser in New Mexico. In 1967 was the first mobile sort of laser, 1 and 2. Then there were a number of stations by CNES, the French Space Agency. And in 1968 was a very famous laser, which was practically hand-built by George Weiss and his group. I will show you a picture of that. VLBI, the first, the Mark I receiver development during that time period. Okay, here is another burn picture, I think. And this is the famous VC4 camera. Now, this is a ballistic camera. The other what you have seen was a tracking camera. The tracking camera can track the ballistic camera stays in place. And in this case, for example, with the pages, as the pages moved across, this shutter here chopped up the trail, and it also chopped up the star trails. And by interpolating the satellite position, the star position, the proper timing, that is great, very accurate directions, and you get 2 directions, the same target basically, right? And basically you have a plane, and if you have 2 of these planes, then you have a baseline. That's really the basis of what you call satellite triangulation. Here is a very similar camera from French, IGN. And here is probably the first geoceiver, Doppler receiver, which basically killed the optical observations. And this was killed, of course, by GPS. Okay, 1960, investigations. Again, in 1966, William Cowler's book was published, The Theory of Satellite Geography. I think this is now the third fundamental book, I think, which really ought to be on the bookshelf. So this is really a theory which is in the book. It's probably used for a very long time by many organizations to develop algorithms for orbit determination, primarily for satellite geodesy. There were some other investigations here. Information geodesy without hypothesis, gravity field statistical investigations by some very famous people, Carla, Diakono, Moritz. Network reliability studies by Professor Varda and Gerhammer. Well, you can have lectures on these things for hours, there's no time. Other investigations, I just want to point out the investigations which led to the first 1967 geodetic reference system, and the least square co-location developed by Professor Kraruk in Denmark, which was a theory about, sorry, nobody understood it. Fortunately, Professor Moritz was always very good at explaining things in a simple way. It literally translated it so that everybody could really understand it. There were some geodynamic investigations already, vertical cluster movements, leveling and gravity by Professor Boulanger. Now, here we go to the gravity fields. In 1962, remember we had only J2 and J3 some time ago. By 1962, we already had J2 through J9, and two of the other more very important coefficients, J41 and J2. 7 years later, in 1969, I had a field which was complete to 16 in the Smithsonian second Earth. Satellite positioning using cameras and Doppler had an accuracy of 20 meters, was absolute 5 meter relative. Nowadays we say, oh, well, we can do this by just looking. In 1969, the first VLBI baseline was observed between Haystack and Greenbank, about 2 meters. And the polar ocean monitoring really started seriously using the Doppler satellites. Well, this is Tranquility Base, where, of course, the first reflector was deposited by Apollo 11. This is it. I've seen this. And we go to the next decade. Okay, 1971 was the Moscow General Assembly. This is the base of the division of the IAG statutes and bylaws for revised. Now, I know that many of you, especially young people, don't really understand the importance of some of these activities which are related to revising statutes and bylaws. But the fact is, as I said earlier, the IAG was always an umbrella organization, an organization where you really could find what you were doing or what you wanted to do and talk to people. So therefore, the structure always had to follow what was going on. Boulanger was the president, and during that time period, 70 and 75, there were really 20 symposia already showing that a lot of activity was already going on. This brings us to the Grenoble General Assembly in 1975, where 51 countries were represented with 410 IAG participants, which is somewhat less than here. But nevertheless, it's an interesting number because most of the IAG General Assemblies, as well as the symposia, had more or less the same kind of participation, indicating that maybe people got older and retired, but somehow they were always replaced by younger. Boulanger, president. Now here is this handmade laser in Athens. And this thing was demonstrated at the first international symposium, use of artificial satellites for geodesy and geodynamics in Athens. And this series of symposia really continued for many years in Greece. mainly to George Weiss. George Weiss, I think, is in here somewhere. I can't really see him because he's demonstrating the thing. There are some other people here you may or may not recognize, but anyway. This is probably one of the first let-alone design interferometer set up. You can see the antenna, of course, and the related things. Now we get to the beautiful places like the first summer school in the mountains. This is again a series of conferences which was organized by, basically by Hans Moritz. Mathematical methods in physical geology. The emphasis was really on physical geology. I don't really have a picture of the participants, but I figure it probably is more beautiful anyway. Oh, I had that already. Okay. General activities, president in 1975-79 was P.J. Kukkamäki of Finland. And of course, in 1975, Michel Louis, who was the assistant of Leblanc, took over as Secretary General. And in 1975, the first Bonfort Prize was given to Eric Gafferan. And the Bonfort Prize was established for young scientists under 40, who really made some significant contribution. And Eric Gafferan at that time received the first one. Also in 1975, the independent review editing of the geology took place, because until then, if you sent in an article, more or less it was published. But after that, it was difficult. Now, here is P.J. Kukkamäki, IAG president, and you can see that something is hanging out from his ear, and that thing was nothing else but his shoelace. And the only, because his theory was that if he puts his shoelace into his ear, it was hard of hearing and people will speak louder. And it actually worked very well. Now this is the first Bonfort Prize winner, Eric Gafferan, his wife. From his expression, I think he doesn't really exactly know where to go from here. Then in 75, 79, the IAG sponsored 28 symposia, and then we get to the 1979 Canberra General Assembly. President-elected was Hans Moritz, and the first Levallois medal was given to Charles Whitten. Now, the Levallois medal was established, at least by then probably Levallois must have passed away. Was established for more senior people who had important contribution to the association. The Bonfort Prize at that time went to Fernando Hans Sons. Now, this is Hans Moritz, IAG president in 1983, again trying to think what to do. Now, there was a wonderful symposium, a joint IAG symposium in Kiev, in Ukraine, in May 1977, which was a mutation and earth rotation began. This was really where things started to develop in the sense that it was started seriously thinking about using the new systems instead of just astronomical observations to determine parameters, earth-rotation parameters, including some of the astronomical parameters. These are the organizers of the symposium. The second one is Professor Yatsky, who at the time was the director of the Kiev Observatory, and Fedorov of mutation fame. Okay, the third Hotin Symposium on Mathematical Geology was in Siena, and here you can see Haruk, right, his name was mentioned earlier, and Klaus-Peter Schwartz and his wife, unfortunately, is no longer with us. And on the right side is Christian Schermer. But anyway, he's here. Oh, there, yeah. Well, he looked different. Now, this is the fourth Cotillion Symposium. And you know, you can just start asking the question, why Cotillion Symposium in mathematical geodesy? This was in the CC 1978, and this was Professor Marussi here. And Channing somewhere. And this is again Channing, Moritz, and Suto, and some others. I think this gentleman is also here. And this is Sanso. So there are many familiar faces. So these symposia are very important. There are a lot of mathematical tools for modeling since you were already curious about Cotillion, you have seen him as a picture of him. He was also one of the brigadiers in the British Army. And well, he basically was a mathematical geodesist. In fact, his book is called Mathematical Geodesy. The only problem with it is that it is in tensor, which I couldn't understand it. I'm sorry, but that's the best picture I had about it. I wasn't sure at that time that the next president will be from. But anyway, internal activities. Let me just say that, okay, so a commissioner for Africa, you already heard about these commissions. This was one of the important ones, really, because what we really wanted to do is to set up a network in Africa, basically to tie the different geometric systems together. But probably one of the most significant establishment at that time was, I think it was called Commission 8, which was the International Coordination of Space Techniques for Geodesy and Geodynamics, short CSTG, which was an IEG and COSPA joint commission. And this commission became really the focal point within IEG of most of the space-related activities, and it existed by latest calculation for 24 years. Every 4 years, the presidency has changed, and most of the former presidents are present. Describe you. And then the next one was Bob Schultz, who's not here from the University of Texas, followed by Gerhard Beutler, who probably doesn't come to these sessions. And then, of course, our organizer, Hermann Reves, was the last one. Now, under the, okay, I will come back to this a little bit later. The technology, inertial survey systems have developed these absolute gravimeters, helicopter-borne gravimetry started. This was the first time probably when people really started to think about gravimetry from moving platforms. And portable Doppler satellite receivers, Magnavox and GMR and others became very popular because they are now all in museums. This is just a picture of one of the inertial survey bands. This here is, of course, the inertial part. The Trainer 2 Doppler system developed, and then satellite laser tracking really really started in Airbus. There were 6 Smithsonian lasers. There were 8 mobile lasers. There were all the intercosmos stations of the Soviet Union. Those lasers into Dyra and in Metzel, of course, in Aurora and Graz. And significantly, the first mobile transportable laser system was developed. Also in the analysis, there were certain breaks, especially in diffraction and waveform digitizing, so that really the accuracy increased to 15 to 20 centimeters, even down to 10 centimeters. The VLBI after the Mark 1, the Mark 2, and Mark 3, see the development of the first mobile system, VRBI system. Lunar laser ranging, Apollo 14, 15, and Lunar Cod 2 reflectors over the moon, 3 of them. The McDonald Observatory started its operation, and the first returns from these things were in Maui and Aurora. A lot of satellites. Most of them are for laser ranging. Probably one of the most significant ones really is this GEO-3. Well, you can argue whether it was the first altimeter or not, but really the first altimeter was Skylab. But this is really the first satellite, let's say, real satellite altimeter. Legios, Legios, like the laser, the big sphere, and then Navstar and CSAT and by 1979, well, the GPS started to sort of emerge. First one was not very impressive, like this, and then this is the launch of the satellite Legios in September 1976. The satellite is still running happily and being observed. This is it here. Investigations in the 1970s. Well, the International Gravity Standard Net was established. I'll show you a picture of that in 1971. This was the first effort really to tie together terrestrial gravity stations. From the mathematical point of view, solution of large systems of equations is very important. One of the pioneers was really nicely lost here, also passed away. And four-dimensional geodesy was propagated by Mueller from Australia, who also passed away, just like myself, in a very early age, unfortunately. So this is the 1971 gravimeter connections. And the WGS-72 was the second geodetic system. The gravity field covariance models started to be used in ocean type models. Well, let's say emerged as something really important. This picture shows the 8 geodetic datums which had to be tied together. At that time, of course, there was no other way of doing it, but triangulation. And this is really what the National Geodetic Survey VC4 network. A lot of satellite projects came about. So you can see there's an awful lot of activity here. ISAJX, which was a French project, right? ISAJX is from CNES. All kinds of acronyms. I'm sure you are tired of acronyms by now. Probably one of the most important was really the NASA Cluster Dynamics projects. They started in 1979 and ended up many, many years later. And the result was published in 2 volumes. And I told you that I'm going to tell you about Henriksen, Soren Henriksen, that first picture. He was the editor. And really, these 2 volumes of the report of the the NASA Cluster Dynamics project contains really work from many institutions which participated there. And I consider it again one of the most fundamental books for learning, which should be really on your bookshelf. Gravity field, we are already making great progress. They are already at 36 degrees, 1300 coefficients. Here are some of the gravity fields published, the GRIN2, the GEM10B. Satellite Doppler and laser positioning improved now to 1 meter absolute, 2 meters relative. This is, this slide is out of order, but this is really the worldwide BC4 satellite navigation network to tie the datums together using the BC4 cameras. VLBI baseline's first transcontinental experiment was between 72 and 79 with East and Boston, and just as importantly, the first transatlantic experiment between Haystack and Boston. Earth rotation parameters from lunar laser ranging half a millisecond. Polar motion from Doppler was about 200ths of a second. And later in the lab program, on the last slides, I will give you a comparison of what happened in 30 years with these numbers. It was truly amazing, and we'll see. Oh, we're getting home. In 1980, the first geodesist handbook was published, and I did not have time to tell what it is, but it's a good book. The IAG sponsored 19 symposia. There was a general meeting just like this in Tokyo, 9 symposia. And then came the Hamburg General Assembly again with the necessity to revise the statutes and bylaws. President Peter Mr. Palm from Australia. Now this is the picture from the second symposium on geodesy in Africa, and if you recognize this very thin person, he's our former speaker. Okay, there's somebody else back there. So, oops, what happened? The third summer school in the mountains. I just wanted to show you that we didn't leave the ladies behind. It's a program specifically for ladies. There are some non-ladies here. And one specifically on the outside of the blue sweater, which will be not recognized. Actually, he still had some dark hair. Okay, there was another important conference, the International Conference, Use of Satellites Tracking Data for Geodesy and Geophysics. This was done in Suzdal in Russia in September 1982. Collaborative effort between Intercosmos and IAG and some of the other organizations. And the two organizers were Surya Tatavian and Sedic. I think Surya is she? There she is. And if you really look at her, you will see that today she looks just like she looked in 1980. Hamburg, 1983. Most memorable because this is when Professor Torge got his, what was it? The, I can't remember, something with the heart. What does they put in your heart?
Pacemaker.
That's it, pacemaker. I must say that after they put the pacemaker in him, next day he was working hard. This was the organizing of the General Assembly. They are almost picking up. Okay. Levallois Medal to Rudolf Siegel, Rumford Prize to John Moore. Recognized by now, hopefully, that the Rumford Prize really went to young scientists, at that time young, who later really became world-renowned scientists. There were 39 symposia. Then came the Vancouver General Assembly, 46 countries, and somebody became president. In 1987, the Levallois Medal went to Arne Bjerkhammer, Rumford Prize to Peter Thyssen, just another example of very clever young people. And in 1988, the International Earth Rotation Service was form, but I'm going to tell you about it a little bit more. There was a general meeting in Edinburgh, it was 5 symposia. Oh, well, you recognize these people on the theory of satellite geodesy and gravity field with some intensive discussion. CC, Chris Reichler and myself and Derek Crawford. This is how we did science. Okay, technology. Sea and airborne gravimetry. With improved navigation with this kind of an accuracy. Gravity gradiometer systems were tested. Superconducting and other types of satellite radiometry to about 10 -4 amperes. And satellite-to-satellite tracking at least was discussed. And the satellite tracking really became extremely important later, and as you know, for this meeting, there is an awful lot of papers on gravity field improvements using these gravitational satellites, like OCA and GRACE, and so forth. But really, of course, they're not, as far as I know, geodetic satellites, because they were designed to improve the gravity field so that the satellite altimeter satellite orbits really could be improved so that the altimeter were accurate. And it's really more like oceanographers, and if you ask an oceanographer, if they consider those satellites oceanographer, or they say software oceanographer. This is one of those little problems. Okay. Satellite laser tracking, it was realized that these laser tracking stations must be mobile. So there is a transportable laser system before, there is a mobile transportable laser system developed, and then there are other lasers in all of these stations. And the accuracy, really, with this kind of improvement in the technology was reduced, but increased, if you like, to 3-4 centimeters, and the GPS timing to 2 centimeters. Then the VLBI, the Polaris and the IRIS network. IRIS was actually a sub-provision of CSTG, which later became the international service for VLBI. In these places, and additional correlator facilities were developed. So there was really a lot of activity. Here is a picture of the transportable laser ranging system, TLRS. And really the way this was transported is like, I guess they just closed this door and they pulled the van together with some other vans, of course. And this one here is the MTRS-1. Where somebody in the picture who looks appearance that it doesn't match it either over the years. I don't know how he does it. It's like that, of course. This was a mobile VLBI system, the MV3. Again, the idea was that this whole thing here could be folded into this platform, and the sides were pushed up in the van. So it was mobile, but now there's some difficulty. Okay, I have to go a little bit faster here. By then, GPS receivers were by 10 manufacturers, probably half of them don't exist anymore, or more, but they were there. And then there were, again, new satellites, mainly really for lasers, and then, of course, the GPS satellites. Okay. The North American Day 2 and the Virgin that System 84, also as a result of investigations during that time. The European Datum in the 87, United European Leveling Network, the International Absolute Gravity Base Station Network, etc. These were all during that time period. Sea surface and satellite altimetry was really guiding speed. And then, of course, the idea of kinematic GPS service that was at line 7. They also saw these meetings and sequence talking and projects. All these projects were really under the CSTG. I'm just going to talk about one. The Married Codes project, which really went for 7 or 8 years. This project was developed to improve that new space systems like the VLBI and lasers, and satellite techniques in general, can really produce Earth rotation parameters just as well, if not better, than the old methods using just traditional astronomy. Merit really stands for, merit stands for monitoring Earth's rotation and intercomparing results. And that's really what it was, because there was a great opposition, especially from the astronomy community, where these new space systems, especially because of there was doubt about the sustainability, should really get officially be involved in Earth rotation parameter or reference level. Codes was for something. Anyway, it has something to do with the reference frame. The two projects were joined, and in 1987, I think it was proved that these systems are better, and this is really when the IH changed to the International Earth Rotation System, which is the IRS, which of course is others. The African Doppler project was also one of the projects, and of course I already mentioned this. This was really a map of the African Doppler project. You can see a lot of stations there. Unfortunately, not this whole, I mean the observations were made, calculations were made, but somehow this thing kind of fizzled out at the end. Okay, now this is almost the last set. I want you to see these numbers, okay? So here is satellite and terrestrial combined gravity fields. Okay, at that time, at the end of the 80s, it was only up to 360. Which happens to be the OSU 86F. And in 1959, we had only n equal 2 and n equal 0. So that's quite a progress here. The GOA determinations regionally, they're about in the order of plus minus 10 centimeters. In 1950, it was only about 5 meters. Locally, this time it was 1 centimeter from about 1 meter. Positioning, space technique positioning, by the end of the 80s was about tenths of a meter absolute and about centimeter relative, down from 100 meters and 20 meters. Now, the Earth rotation parameter is down to about a milliarc second, from about 200ths of a second in 1970. So this progress clearly was made, of course, by people who were looking at the observations, trying to explain what the observations should be, proving them one up, improving again the technology, and they came up to all these meetings to discuss and get some new incentives to talk to each other. And so I suggest that you read this. But I think this is probably the key here. Shared concerns creates ties of friendship. It transcends jealousies and ideologies. And these are very powerful forces for scientific progress. Thank you very much.